now. So 6.5, Bode Plots. And unlike the biology professor, it's Bode. Bode, not Bodie. Robert Bode. Anyways. Given equation 637, which I know you guys have all committed to memory, it's the big one. It deserved a box, remember? It was important. It said that if you put in a sinusoid to a system that's linear, you get out a sinusoid, okay? And at the same frequency as the sinusoid you put in, with the same amplitude multiplied by the magnitude of the frequency response function, and the same phase, but added to the phase of the frequency response function. So, if you remember that, that's good because it's kind of an important thing. So this is, given the importance of that, we're most interested in the magnitude and the phase of the frequency response function. Each of these is a function of angular frequency omega. So plotting the magnitude of h of j omega versus omega and the phase of h of j omega versus omega is quite useful. Bode plots are such plots with axes scaled in a specific manner. Okay, so there's really nothing magical about it. It's just the plot of those two things. So we'll expand on that a little bit. A Bode plot is a useful graphical representation of the frequency response of a system. Let the magnitude of u of omega, which is the magnitude of the Fourier transform of the input, right? And the magnitude of the Fourier transform of the output be the complex amplitudes of the input and output, respectively. Recall that the magnitude of the frequency response function, h of j omega, can be expressed as, whoa, really big. It's just plugging in the definition of the frequency response function, y of omega over u of omega. This is the ratio of amplitudes, so it is akin to amplitude ratios commonly expressed in decibels, okay, dB. However, the magnitude ratio of equation 638, which is this, but, oh yeah, there it is, says it right there, 638, is not dimensionless, and therefore cannot be expressed as a decibel in the strict sense. So, have you seen decibels before? Yeah, I thought you guys had seen them. Yeah. Nevertheless, it is standard usage in system dynamics and control theory to use the familiar formula to compute the logarithmic magnitude. So we still use the regular dB formula. So 20 log base 10 of the magnitude of h of j omega. And we say that this is in dB, even though it's like kind of like in quotes dB, because there are actual physical units in this magnitude ratio. So h of j omega actually has units, because the output doesn't have to be in the same units as the input, right? So like your output could be in newtons, and your input could be in volts. So you could have newtons per volt, right, as the unit, and then you're going to take this log, and then you're going to say it's dB, which is a little bit of a scam, right? It's not a real, true dimensionless ratio that we're taking the decibel value of. So it's kind of weird that we do it. It's just been common practice for so long that people just do it. So I don't know what to tell you. It's awkward. Just, pretend like it makes sense, it does make sense to use some sort of logarithmic scale, and we'll see why. We're able to draw sketches of these Bode plots without too much trouble in a logarithmic scale. Okay. The phase is usually plotted in degrees, and the omega axis is logarithmic in both plots. So we plot on the horizontal axis omega, and we have that be logarithmic in both cases. In the magnitude plot, we plotted in dB, this weird dB, and then the phase plot, we plotted in degrees. So, I mean, it's really just like a lecture on how to plot something, which is kind of weird, but we also learn how to sketch, which is actually a really useful thing to understand because it gives you a little bit of intuition on what a transfer function is going to look like as a frequency response function. Okay, so the two plots are typically tiled vertically with a magnitude plot above the phase plot. So if we were to look at it like this, it would be magnitude plot and then phase plot. And they're both functions of omega. So this is the Bode plot. Put them together. So that's what we're going to do. We'll work a simple example. Let a system have transfer function h of s equals s. So it's just a single zero at the origin. Okay. Find the frequency response function and draw the Bode plot for the system. So we'll use the definition. Well, actually, what we'll do is we'll say we can compute the frequency response function from the transfer function very easily by just plugging in s equals j omega, right? And we're just going to plot it. So h of j omega equals h of s evaluated at s equals j omega, which is just equal to s evaluated at j omega, which is just j omega, right? So we have our frequency response function. Now we need to find the magnitude and the phase, right? So just to think in the complex plane, real quick, real, imaginary. This is all imaginary, right? This is the j term, omega, so we just have, if I use a different color, then we would just have, omega, and it's in the j direction. So that's what we've got, and we need to find the magnitude and the phase. So you can pretty much just do that by inspection. I think we could all figure out that by inspection, right? The length of this is omega. So we could say, switch back to black. So we would say that the magnitude of h of j omega is just equal to omega for positive omega. And we're just going to do our Bode plots almost exclusively. We'll just use positive frequency for them. So if omega is positive, then the magnitude is just omega, right? The length of this is just omega. The phase, so the angle is going to be the angle from the real axis, right? So there's my angle. What is that? 90 degrees. I guess that little degree symbol is deprecated now. I don't know. Somebody told me that. I don't know if it's true. Could be true. Fake news. Oh. It's an awkward thing to bring up these days, fake news. People are like, oh, what does that mean? What does that mean? Does that mean you're a Trumper? It doesn't mean that. It doesn't mean that. Okay, we just need to plot it now, right? So, this one's going to be our magnitude. And this is going to be our phase. And oops, a little long. So remember, our omega is logarithmic, which is why when you guys are asked to sketch these in your like exams or whatever, I'll give you guys something with a logarithmic scale typically. Otherwise, I'm not going to be super strict on what they look like. Because remember, a logarithmic scale would look like, you know, something like that. And then, so it's kind of hard to sketch freehand. At least, you know, have engineering paper, graph paper, it helps. So the magnitude is in dB, right? So 0 dB, you may recall, is just a magnitude in non-dB units of 1, right? So then we've got this this omega as our function. So it's just a linear plot. And actually, so something that is linearly increasing or decreasing in a logarithmic plot, or in a non-logarithmic plot, is also linear in a logarithmic plot. So it's going to be a linear function, it's a log-log plot. And it's going to have at omega equals 1, it should have 0 dB, right? So we'll say this is our omega equals 1. So 10 to the 0, omega is equal to 1 when it's equal to 10 to the 0, right? So that is going to be our crossover point. And it's going to be going in a linear fashion here. And I'm going to just draw a straight line and scale it afterwards. So I'll say this is the line. Maybe I'll change the color so it's a little more clear. So this is our line, and it turns out we can find out the slope of this and stuff, but I think it's actually a little bit of a distraction to talk too much about that at this point. So it's a linear function. If you plotted it, it would go through omega equals, it would go through 0 dB at omega equals 1. And then the phase is just 90 degrees, no matter what the frequency is, right? So, did I alienate a bunch of people with the Trump comment? I'm sorry. I didn't mean to alienate you. Sometimes I don't know. People get kind of sensitive about political stuff. I like to joke about it. But not everybody likes to joke about politics, so my bad if I offended anyone. I really wasn't trying to. Okay. So the plot is pretty simple, right? I mean, we're just plotting the magnitude and the phase of the frequency response function. So we can just go back to what the frequency response function is and find the magnitude and plot it, and find the phase and plot it, right? There's nothing magical about the Bode plot. You could just go to the definition of what it is and do it. However, we're going to learn how to sketch them by hand because it gives us an intuition when we look at a transfer function what the frequency response function would look like. And that's important to be able to develop. Not because we don't have MATLAB. Remember, we have MATLAB. We always have MATLAB. It's just that we don't want to be reliant on that to gain intuition when we look at something. We want to be able to have that intuition still when we look at a transfer function. We shouldn't have to type into MATLAB something and then just be like, I had no idea that was going to come out. Because I don't know about you, but occasionally don't program things perfectly. It's very rare that I will have a bug in my code. Martine is laughing because it's not true. He's in my embedded computing class, and I was just chasing down a bug for like 4 days down in the code. Yeah, that was good times. Okay, so yes. It turns out that when plotted on this logarithmic scale, recall the omega axes are always plotted logarithmically. Both magnitude and phase are quite asymptotic to straight lines for first and second order systems. Okay? So for first and second order systems, these are pretty close to being straight lines, not the whole time, but they could be like a straight line here and a straight line there and a straight line here. So, well, that wasn't very straight. But straight lines in different regions. So that's an interesting fact. So for first and second order systems, that's pretty true. Furthermore, and so that first fact was interesting. Oh, okay, for first and second order, but it doesn't apply above that. However, higher order system transfer functions can be rewritten as the product of those of first and second order. For instance, what order is this transfer function? These are like blanks because I didn't want to put in big numbers. Third order, right? The denominator has polynomial order of 3, making it third order. So it's third order, and I'm saying, okay, you could break this down. Okay? It could be seen as being the product of multiple transfer functions. So this numerator, let's pull that numerator off and let's make it its own little transfer function that we're...
Yeah. Need to go home. Let's just all go home. It's time.
It's time. Okay. We got this. I believe in us. We can make it through. And then we're going to party for a whole week. Okay. In order to pull this out, I wanted to get this into this sort of like tau s plus 1 form. So I factored something out. So there's a constant that I pulled out. I also, in this denominator, I'm going to say that we could factor this denominator out and make it look like, if it's third order, I can pull out a first order and leave a second order there. Potentially it's second order. Maybe I can even factor that, depending on if it would be complex or not, if I had to factor it. If it's real, I would want to factor it out into first order systems. If it's complex, I would leave it as a conjugate pair and leave it second order. But essentially, I'm showing you that you can rewrite this as a product of first and second order systems. Okay? So that's the big idea there. Recall from, for instance, phasor representation of things, that for products of complex numbers, phases phi add and magnitudes m multiply, right? So we remember that. For instance, if we had a magnitude of something, so magnitude 1, phase 1, so this is like a phasor form of something. This is representing, say, these two together. And then 1 over m1 phi 2, so then this would be representing this guy. And then 1 over m3 phi 3, so this would be representing this guy. If I had those, the magnitudes would multiply / divide, right? And the phases would add / subtract. Okay. If it's in the numerator, it multiplies or adds. If it's in the denominator, it divides or subtracts. So we're familiar with that way of combining things. And if one takes the logarithm of the magnitudes, they add. For instance, if you took the logarithm of m1 over m2, m3, That's just using your good old-fashioned log properties that you learned in high school? I don't know. When do you learn log properties? Never. You never learned them. Okay. You take, the logarithm of a numerator term, subtract logarithms of the denominator terms. So there is only one more link in the chain. First and second order Bode plots depend on a handful of parameters that can be found directly from the transfer function. Okay? There is no need to compute the magnitude of h of j omega or the phase of h of j omega in order to construct the plots then. Okay? And that's like kind of the big, you can go straight from the transfer function to starting to sketch your magnitude and phase of the frequency response function. You can go straight from your transfer function to sketching the Bode plots, which is what we're going to learn to do. And it's like the big main thing that is sort of like the punctuation at the end of this section for the test that we're coming to. Who won that, by the way? I didn't even look. Who won the vote? Friday won, so it's still next Friday.
No. Technically.
Or not next Friday, but
Technically. Let's go.
15 to 14.
It's 15 to 14, 323 versus 326. So we have to suffer for another weekend before we take it.
okay, I will entertain votes until I check it, which will be at 12:15.
And I have a convenient list of people who voted for.
There you go.
Next door.
Yep, kneecaps.
Yeah.
Okay,
So let me hear test stuff.
so let's get back to this. So in a manner similar to the example, we construct Bode plots for several simple transfer functions in this next little section here. Once we have these simple building blocks, we will be able to construct sketches of higher order systems by graphical addition because of logarithmic magnitudes and phases combined by summation. So because they combine by summation already for phases. So phases are already additive. So we don't have to even do any logarithm stuff to them. But if we take the logarithm of the magnitudes, they also add. So we can do this graphical addition of these building blocks. So we just learned to sketch the simple building block ones, the first, second order ones. And once we've got those down, we can do higher order systems by just graphically adding these first and second order ones. So it's going to be good time. Lots of fun. So, Bode plots for simple transfer functions. We need the building blocks first. Constant gain is our first one. So for a transfer function that is simply a constant gain, h of s equals k, the frequency response function is trivially h of j omega equals k. Okay? If you plug in s equals j omega to a function that doesn't have s in it, not a lot happens. Its magnitude is just the magnitude of k. For positive gain k, the phase is 0. And for negative k, the phase is 180 degrees. Okay? Not too bad. Okay. Pole and 0 at the origin. So we already have constant gain, Bode plot, easy peasy. Pole and 0 at the origin. Okay? So in that example that we did, we already demonstrated how to derive from the transfer function h of s equals s, a 0 at the origin, the frequency response function that's plotted in figure 6.3b. So that's this guy right here, right? We already drew that in the example. We already learned how to do that. So if you wanted to do the same thing for a pole at the origin, that has a transfer function of 1 over s. So you plug in s equals j omega. Very similar to the h of s equals s case. The frequency response function for that is plotted in figure A. So it's the same, it's just it has this a negative slope instead of a positive slope. It still goes through at omega equals 1, it has 0 dB, right? and it has a slope, importantly. So look at, in 20 dB, it went from 10 to the minus 2 to 10 to the minus 1. And in the next 20 dB, it goes from 10 to the minus 1 to 10 to the 0. It's got a constant slope. It goes, we say it goes negative 20 dB, and then we call a factor of 10 a decade. Okay? So negative 20 dB per decade is the slope. And that's the same with this one here. It goes from 10 to the 0, for instance, to 10 to the 1. And it goes up 20 dB. So it has positive 20 dB per decade as its slope. The phase of this one is negative 90 degrees. The phase of this one is positive 90 degrees. So they're very similar. They're kind of like duals of each other, right? So check off those building blocks. Yes?
On the example that you showed before, why was the intersect point right on the 10 to the 0 right there versus those?
Yeah, so I drew the axis at 0 dB, whereas down here I'm doing this like framed axis instead. So 0 dB is in the middle of the graph now. Yeah, it's typical, I would say, to draw box frames around your Bode plots, but that's not a fast rule. You can play with that a little bit. When you freehand sketch, it's hard to draw it with a box. So, okay, excellent. So real pole and 0 is the next one. The derivations for real poles and 0 are not included, but the resulting Bode plots are shown in figure 6.4. So I didn't go through the derivation of these. It's not hard, but our takeaway is we get how to find them. We just have to plug in S equals j omega, find what the magnitude is, find what the phase is, take the dB, and plot it. So, but what's cool about this, so I'm plotting this, the tricky thing that's happening here is I'm plotting one plot for a real pole and one plot for a real 0, right? So, I mean, one pair of plots. And this actually is true for all cases of the transfer function looking like this or like this. So how am I doing that? For different values of tau, this should look different, right? I'm doing a little normalization on the axis, which is a very common thing to do. It's also in the book, so something that you should definitely buy into because there's no other way it's ever presented because it's really nice. So instead of representing these as being omega on the horizontal axis, we're using the product of omega and tau, okay? Where tau is that time constant. It's really useful because when you plug in S equals j omega, tau and omega always show up together. So when you plot it, if you plot tau and omega together, you only need to do one plot, and it works for all of the different taus. If you had to, see what this would look like for a specific tau, then you have to essentially stretch or compress your horizontal axis, right? Just how when you guys were first learning how to do plots of like f of x, and then they were like, what if you're doing f of 5x? What does your plot look like? And you had to like squish it. Remember that? Did you guys ever do school before this? You guys just will never admit to ever having learned anything before this class. It's pretty funny. I was at last night. I'm part of this like South Sound Robotics Advisory Board, and like a lot of high school teachers and then some other professors and stuff. And it's really funny talking to them about like, what do we need to teach the students at the lower levels? And I was just cracking up. I was like, they won't admit to learning anything. Like, I know you teach them these things, but they won't admit that they know. Like, you say, like, you guys learned this before, right? You guys did a good job saying new DB. That was good. Maybe it's beneath you to say that you know how to do stretching analysis. I don't know.
Keep your expectations a little bit.
Yeah. I have very high expectations of you guys. I know you guys can do awesome things. So we've got this one plot to rule them all for each case, right? One plot, and so it's instructive to look a little closer at these. So when tau omega, which is these horizontal axes, is equal to 1, something happens in all of these plots, right? So that's tau omega equals 1. So it's like this, like a sort of key point in these plots. And that is true when tau omega equals 1, tau omega equals 1, which implies that it's true when omega, which is what we're typically going to be using as our horizontal axis, right, is 1 over tau. Yes. And this we call our break frequency. Break frequency. And that's really important for not just for these real poles and zeros, but also for the next type of system too. So this frequency, that's a really crucial frequency, happens at the break frequency. So we know that this magnitude plot goes from 0 dB at lower frequencies. At the break frequency for a real pole, it then breaks off and approximates this other linear function. And that is a line that has a slope of approximately, at least later on, it approaches negative 20 dB per decade. Okay. So you got to find where this break happens. You got to find, then you know what the slope is above that break. You know what the value is below that break. And you can sketch. This intersection, so you notice that it's not really a sharp angle here. This is curve that happens. This happens at negative 3 dB. That crossover. So when a lot of times you'll sketch with a straight line and then you'll round them off. And you just go through negative 3 dB, and that's considered to be pretty good. Okay. The phase plot is 0 until you get up to 1 decade below your break frequency. And then it has a slope that goes and meets up with 1 decade above the break frequency at negative 90 degrees. It goes through negative 45 degrees at your break frequency. And so we would just draw a line, a straight line. Not very straight, but a straight line approximation of what it does in between those two, and then it flattens off to 90. So our straight line approximation is 0 until a decade below the break frequency. Then you're going to take a line that intersects negative 45 degrees and goes down to negative 90 at 1 decade above the break frequency, and then it's flat after that at negative 90. Exactly the opposite is true for a 0. So the pole stuff, just invert that and you get the 0 stuff. Okay? All right. Now we're to the last one and the most complicated one. Complex conjugate pairs of pole and 0 pairs. So the derivation of complex conjugate pole pairs and 0 pairs are not included, but the resulting Bode plots are shown in figure 6.5. We're mostly concerned with sketching, so we're going to talk about how to sketch these. This is the hardest ones to sketch. Notice that I have a scaled horizontal axis again, right? this time I'm dividing omega by omega n. Omega n is the natural frequency of the second order system. Is that a good question back there?
Oh, sorry.
Okay, no, that's cool. I just wanted to make sure I wasn't just ignoring you. So, cool. Omega over omega n is the scaled horizontal axis. This allows us to draw fewer, so for every different omega n, we don't have to draw a different plot, which helps. However, we still have zeta, right? So if our transfer function looks like this, and notice specifically, you have to have an omega n squared in the numerator. So if you don't have an omega n squared in your numerator, what can you do? Are you screwed? No, I mean you're screwed, but also you can still do something about this problem. Yeah.
It into two different functions because it's third order now, and you separate it to a first and a second.
Yeah, so you could contrive to have an omega n squared in the numerator. So say you had 1. You could multiply it by omega n squared divided by omega n squared, but save the divided by omega n squared out front, and that becomes a constant transfer function by itself, right? So you got to get a little tricky, just like with tables. You have to make it look like the table, so you have to start factoring out things or multiplying by things and rearranging things to make it look like that. Always using, of course, proper legal algebra techniques that are true. And so this is the result. So if you have one that looks like this, you've contrived it to look like this factor in your overall transfer function. It starts out at 0 dB at low frequency. The break frequency is once again when omega divided by omega n is equal to 1. So in this case, it's here and then here. So this is our break frequency. Sometimes we subscript b for break. In this case, it's when omega over omega n equals 1. So it's when omega is equal to omega n, right? So our break frequency is a natural frequency. It makes sense. We talked about how natural frequency is such an important quantity, right? You can think of it as being the frequency at which the system wants to oscillate, okay? It's natural frequency. And we've talked a little bit about resonance ideas before, right? So this is not a lot. This is something you're going to get into more and more. We'll talk about it more and more in the coming weeks, but in vibrations class, you'll talk about it a lot, okay? But the idea is that when you get near that natural frequency, if your zeta is low, like zeta equals 0.1, which is the blue line, you're going to get this peak that happens there. What does that mean? What does that mean sort of physically?
It's a resonant frequency.
A greater response, bigger.
Yeah, so resonance, you often hear people refer to it as resonance that's happening. It means that, so this is the magnitude of our output over our input. When you get greater than 0 dB, that means that the output is greater than the input. So if you put in a sinusoid at near the natural frequency of a second order system with a zeta of 0.1, you're going to get an output amplitude that's greater than the input amplitude. The lower zeta is, the greater that output amplitude is going to be. So when you have a system that has resonance in it, so it has a resonance frequency that is very sensitive, that has low damping associated with it, you could put in a really small forcing at that frequency and you're going to see a really large response. So that's sort of the very beginning of our thinking about vibrations and about resonances, and that sort of idea has a lot of power to take you a long way as far as analyzing these systems from a sort of vibration perspective. If you're wondering, this class is sort of like the precursor to vibrations class. So vibrations class will sort of build on this stuff. So we get this peak, and you have to say, okay, what is my zeta? When you're trying to do this magnitude plot, you say, what is my zeta? okay, if it's like 0.2, it's going to be, it's going to have a peak between the blue and the orange. So I'll say my peak is like this. So when I draw my sketch, I'll say it's 0 below this. And then it's going to have some peak, so I'll draw it coming up with a hump there. And then above my break frequency, they all kind of come together to one asymptote, which has a slope of, and it's not totally obvious from this, but the slope is negative 40 dB per decade. I know a few of you have to go a little early because you've got a test, right? So no worries. So the negative 40 dB per decade above the natural frequency, above the break frequency, is what you see. So when you do the sketch, that's what you draw. On the phase plot, when you have, this one's a little tougher, but typically what we'll do is say if you have low damping, we say it's 0 degrees linearly, or as a straight line, up to the break frequency, at which it goes down, it drops 180 degrees, and then it flatlines at negative 180 degrees. And then you round it based on what your damping is. So if you have really high damping, this is very bad approximation, so you have to round it a lot, right? So like zeta equals 0.9, you have to do that, which is like a huge rounding, right? But zeta equals 0.1 or anything small, and it's going to be like that. So that's our straight line approximation for a second order complex conjugate pair. If you can factor them out, and there's real factoring of them out, it's not a complex conjugate pair, it's a real pair, and you could just treat them both as first order systems. You can decouple them. You can go back to these guys. You just do 2 of these instead. Okay. Sketching Bode plots, this is what we're going to end with. We can use MATLAB's Bode command to create Bode plots from LTI system models. So, if you want to check your homework on this, I encourage you to do it. Define a transfer function. Define the transfer function in MATLAB. Use the Bode command. Just say Bode of whatever you define the system to be, and it'll just plot it for you. It'll just give you this plot. However, we must understand how these plots relate to their transfer functions. In this section, we learn to sketch Bode plots in order to deepen our intuition. So let H be the product of a bunch of transfer functions. That is, let H be the product of several factors, HI. The magnitude and phase are the product of the magnitudes and the sum of the phases. Bode plot, remember, we used the dB definition. So if you take the Bode, or if you take the log of a product, you can instead turn it into a sum. So now we've got a sum and a sum. Which is what we wanted. The result means we can graphically sum both the magnitude and phase Bode plots of the individual factors of H, as long as we're adding magnitudes in dB. So that's the way of going about it. That's the method that we use. So I'll do an example or two. I'll either upload them over the break for you guys to study them, or I'll do them when we get back on Monday. Yeah.
Are you gonna post some solutions of last homework too?
Yes. If I haven't by like tomorrow, just send me a message on Slack and I'll do it. I sometimes forget if I'm not in front of my. Any other questions? Have a good break.